All right. So today we're going to actually try to make some sense of all these different reactions that we've been looking at. And so I'm going to talk to you about, whenever this comes up, I'm going to talk to you about, there we go, about organic synthesis, right? And I want to put it, but I want to do it in the context of stuff that you've already seen before, like, or know about or heard about, make it practical. So what I have on the screen is actually a list of reactions that we've learned. Hopefully, now by this point, you should have flashcards for these reactions too. Uh, but we've talked about double bond synthesis, how to make double bonds, right? You can do dehydration or you can do elimination of HX. We talked about double bond reactions, halohydrin synthesis, halogenation, electrophilic addition, oxymercuration, hydroboration, ozonolysis, osmolation, hydrogen. We talked about all these. The only reaction that we didn't get to is diol cleavage when we were talking about osmolation. I'm going to show you that in this presentation. And then we also talked about triple bonds using, lithium or um, Lindlar's catalyst to do cis or trans reduction to alkenes. Talked about, excuse me, hydrogenation. We talked about oxymercuration, uh, hydroboration to the enol, and then the enol tautomerizing to give you the keto form with either one of those two reactions. And we talked about acetylide formation, right? Taking the triple bond and deprotonating it using a strong base, and then either reacting it with something that's primary to do substitution or something that's secondary or tertiary to do elimination. So all this stuff we've talked about in the last 2 weeks. So let's talk about how all of this relates to synthesis. So the first question is, what is synthesis? And it's basically the application of organic reactions to get our target, a chemical target. Sometimes the target is a big giant molecule, which we're going to see later. Sometimes it's a small molecule or a fragment of a giant molecule. It just depends. But the reason why we do synthesis and the reason why all these reactions are important is because organic chemistry is ubiquitous, right? It touches everything. If you take vitamins, most of the times the vitamins are synthetic. They're not derived from natural products. They're not derived from, your vitamin C is not being derived from, the Oompa Loompas in a lab squeezing oranges, and then you get the vitamin C out of the orange juice, right? A lot of your vitamin C comes from synthetic sources. So pharmaceutical companies, they do syntheses uh, with an aim toward drug discovery, with an aim toward innovation, with an aim towards taking something that you find in nature in very small amounts, like aspirin, right? That comes from the bark of the willow tree. There's not enough willow trees in the world to make enough aspirin for consumption, of the entire world. So you got to find a way to do that. So pharmaceutical companies do that. Industrial chemical companies do syntheses and do method development. Right? Think about I talked about this with my earlier class. Something like making Roundup. Roundup is not a natural product; it's synthetic. It is used as a herbicide around the world. Same thing with if you have an exterminator. Their pesticides are not natural; they are derived or analogs of natural products, but they're not naturally derived. Right? A lot of that stuff is synthetic. So, and then you talking about academic research, then a lot of times, well, in academic research, we do synthesis to innovate, right? We might see an existing reaction and develop a new way to do it. Or we might see an existing reaction and develop a faster way to do it or a more efficient way to do it. So, and when you do organic synthesis, you can do, it's two things that are critical. You either do a method development where you're developing new reactions to do or new ways to do pre-existing reactions, or developing new reactions, or you can do what's called total synthesis, and that's a stepwise synthesis of a larger, more complex molecule, right? And total synthesis can be done in two ways. You can do convergent synthesis, which is taking smaller fragments and bringing them together to make a larger molecule, or you can do linear synthesis where you start with a fragment and you just keep adding pieces to it until you reach your target, right? Both of those are done every day in labs all around the world. All right, so let's look at again the thought process behind synthesis. So every synthetic undertaking requires a lot of planning, right? That's where the chemical literature comes into place. You need to be able to search journals. That if you did the aspirin exercise that I did with the references, you multiply that by 100, right? You're looking for articles or journals that have precedent. If I want to make this compound or do this particular reaction, what's the precedent? You know, and that's where the planning part comes in. And you need a not working knowledge of different reactions that you have available. That's why I encourage you to make flashcards. So if I ask you, give me 3 ways to make alcohols, well, you know 3 ways to make alcohols because we talked about more than 3 ways, right? Or if I ask you, give me 2 ways to make halohydrons, well, you got 2 reactions available to you. So the other part of of organic synthesis or part of the planning process is doing what you call retrosynthesis. And that's where you look at the final product and work backwards, right? So you ask the question, what did I start with to get to this existing product? So we're gonna look at a few examples on that, doing retrosynthesis. Then we're gonna jump into some real world stuff, right? So if I have this molecule that's shown here on the right, 2-hexene, cis 2-hexene, right? The cis part is important. And I wanted to start with 1-pentyne. The question is, how can I get there, right? Sometimes you need more than one step. So if I look at cis 2 pentene and ask the question, what is the immediate precursor to this double bond, right? Based on what we know, the immediate precursor could be a triple bond, right? That looks like this, right? And then if I treat that triple bond with under hydrogenation conditions and Lindlar's catalyst, then it'll give me a cis alkene. Why do I need Lindlar's catalyst and not just hydrogen gas and palladium? Because if I use another method, I'm not going to get the stereochemistry that I want. I want my double bond to be cis. So I need to use a reaction that's going to guarantee me that stereochemical outcome. Now the other question is, where does this come from? Right? The alkyne that I'm using, right? And again, you can take that alkyne and envision making it from acetylide anion formation followed by substitution, which we've already done, right? You take 1-pentyne, and then you react it with a strong base to get the acetylide. And if you treat that with an alkyl halide, a primary or methyl alkyl halide, like it's shown here, methyl iodide, is going to give you this alkyne, right? So the overall synthesis will look like this, where you have the alkyne, you treat it with a base, and then you follow that up with methyl iodide, and then you follow up that reaction with hydrogenation using Lindlar's catalyst, and that'll get you to this final product, right? Any questions about that? So you're always thinking backwards. If you're doing a retrosynthesis, your goal is to look at the product and work your way back to the original initial start material. All right, let's look at one more. Let's take this for instance. I want to synthesize 1-hexanol from acetylene, all right, and an alkyl halide. Again, I need multiple steps. So the precursor to the alcohol, you could think about that if you look at the alcohol structure right here, that these 2 carbons here and here, one precursor to that would be to make that from an alkene. And we know ways to do that, right? So if I can, if this is my product, I can say, well, I know that I can make alcohols from alkenes. That's one way to make it. There's a lot of ways to make alcohols, but I know I can make alcohols from alkenes. So the precursor to this alcohol would be this alkene, right? And if I take that alkene and react it with, if I do a hydroboration slash oxidation on it, then I'm able to get to here. Are y'all following that so far? So the precursor to the alcohol is the alkene. And then we can also ask the question, where does the alkene come from? Right? We got ways to make alkenes that we haven't talked about, but we also have ways to make alkenes that we have talked about. We could take a alkyne and hydrogenate it down to the alkene, right? And so when we think about this in totality, how do I go from here to here, right? I need more steps. I need more than one step. First, I need to start with an acetylene, treat it with a base, and then add an alkyl halide. That's going to get me to here. And then I'll take this, treat it with Lindlar's catalyst. That'll get me to the alkene. And then I take the alkene and treat it with, or do hydroboration on it, followed by oxidation, and that'll get me to the alcohol. So anytime you're doing a synthesis, unless it's a immediate product, sometimes you have to work back and it may be multiple steps. But again, this is just to illustrate something we talked about earlier. When you're doing reactions, the first reagent is going to work on this, right? And anything subsequent to that is going to be on working on the product of this first reaction, right? Not this itself. All right, we're going to skip this one. All right, so now let's look at some synthesis and with some real life application, real world application, right? So the molecule that you see down here, this big monster of a molecule, is Taxol. Taxol is an anti-cancer drug discovered in 1967, discovered from an extract from the Pacific yew tree. Now, I want you to think about why synthesis is necessary right here. All right, so if in order to treat one patient, you need 6 trees that are 100 years old to harvest, to take the bark and extract out the Taxol from the bark, right? You will never get enough Taxol to give to every cancer patient who needs it with this method. So you got to develop a way to make it, right? So you need a way to make it. And the way you make it is through total synthesis, right? You have a target, you know what the structure is, and then you develop a method to get to that target, right? Well, my wife, before she passed, this was the first treatment that she took. She took Taxol and doxorubicin, which is another anti-cancer drug. She took them together. And but the Taxol itself didn't come from the yew tree. It came from somebody developing a way to make what came from the yew tree. So that's why, again, why synthesis is so important. And you got 2 people that basically pioneered this synthesis. Casey Nicolau, I think he was at Harvard, and then Robert Holtman at Florida State. And in 1994, they were basically racing to see who could finish this first, right? So the Nicolau synthesis is shown down here, right? And this is the retrosynthesis. So this is the target. This is the fragment that he started with, and he worked his way backwards. Well, worked his way forward to the target. So here, where you put these 2 fragments together, and then to here, and then from here to the final target. This is what you call a convergent synthesis, right? The convergent synthesis takes smaller fragments and you add them together, right? And then linear synthesis takes an initial fragment and you just keep building on top of it. All right, so that's the Nicolau, basically retrosynthesis. And then for the Holtman retrosynthesis, this is his initial start material. He started with this bicyclic system right here, and then he just kept adding to it, kept adding to it, kept adding to it until he got to the final product. So the Holtman synthesis was much more efficient than the Nicolau synthesis, and so he was able to patent it. And look how long it took him. He started working on this in 1982. He finished it in 1994. Now, when I say he started working on it, I'm not saying that he did it himself. You got to understand how, when you're in academia, how it works. You're talking about 12 years, so that's at least 3 PhD students, excuse me, at least 3 PhD students. That's at least, you could say 6 postdocs, because postdocs normally stay about 2 years. And then multiple, probably undergraduate researchers, students coming in, doing research as a part of their chemistry major requirements or biology major requirements. So it's not him per se. He's more like the CEO of a lab, right? Now, not to say he didn't have something to do with it, because a lot of the ideas and a lot of the uh, initial, uh, journal articles and things like that, they always come from the top. But it's up to the graduate student to take what's there and kind of run with it and innovate from there. But 12 years to synthesize that. So he took that license, he took the patent, and he sold the licensing uh, to Bristol Myers. Now, this was in 1994. I think I put this talk together several years ago, and he had earned up to over $200 million just off licensing alone, right? Licensing out his synthesis to this pharmaceutical company, all right? But the synthesis itself is linear, right? He started here and he never added other fragments. He just took that and just kept building on it, right? And he published it in the Journal of the American Chemical Society in 1994, right? As a full, I think it's a full paper, because you could publish either a full paper or a communication. It just depends on the length of it. All right. So now let's look at some stuff here, right? So this is one of Holtman's fragments. And you might look at that. Let me go back. You might look at this and say, oh my gosh, this is so complicated. It's so complex. And it is. And one of the things that makes it complicated is the presence of all of these chiral centers or stereo centers, right? This OH is going back into the page. This is coming out of the page. That's going back. This is a bowl, so it's coming out, so on and so forth. That matters, because any stereoisomer is either going to have a positive bioactive effect, or it's not going to have any effect, or it could be negative, right? So when you take in Taxol, you want this isomer. You don't want another isomer, because it may not work or it may kill you, right? So that's another part of synthesis that makes it a little bit more difficult when you're synthesizing natural products, is that you got to get the stereochemistry right. Right. So all your reactions that you do, you have to have you have to generate the proper stereochemistry in in whatever product you make. All right. That's very important. Sometimes you can use the pre-existing stereochemistry to guide it. Other times you need a catalyst, right, to make sure you set each stereo center with the proper configuration. All right, so let's look at something real quick. Now, this is stuff that we've done already. No, we haven't made Taxol, but we know some of these reactions. We actually know a lot of them. So how do you think he went from here to here? Tell me, based on something you learned this semester. If you an undergrad researcher working in his lab, what would you recommend for him to make this diol?
It's like assimilation.
Speak up. Who is that?
I said like assimilation. I know it's something elation. And it has
Some lation, some kind of lation. Is that what you're talking about?
yes.
Osmolation?
Yes.
Yeah. Isn't that a way to make diols? Now, here, would it matter that the diol is syn? Tell me why not? Because osmolation does give you diols, and it gives you syn diols. So tell me why or why not the sin part would matter here. SYN now, not SIN.
I don't think it matters because they aren't on the same side.
Okay, but why doesn't it matter? You're right, it doesn't. What is it about the alkene that makes it not matter? You're absolutely right.
Is it because there's another alcohol on the other side?
Mm-mm.
Oh, just kidding.
That's okay. That's a good answer, but that's not the answer. Think about it. What if this
Because of
out?
the
What if?
box?
Huh? Say again.
Is it because of the box?
No, the box is my decoration.
Oh.
That's just me pointing it out, emphasizing. What if
Dr.
this?
Russell,
Go ahead.
is it because it's a terminal?
Who is that?
Christina?
You're exactly right. It's terminal. So this carbon right here doesn't have any stereochemistry. That's 100% correct. If I had done this alkene over here, it would be different, right? Because then they would have to be either both wedged or both dashed. But here it doesn't matter because it's terminal. That's exactly right. That's a great answer. All right, but do you see again all this complexity? And this step is done with a simple osmolation. All right. All right. What about here? What do you think? Right. I went from here to here. Right. Do you think that is what type of reaction is that, by the way? I'm trying to give you a hint. Just watch the cursor.
Substitution?
Oh yeah, it's a substitution. Thank you for reading that for me. I appreciate it. Yes, it's a substitution. We studied substitution. What types of substitution we studied this semester?
E1 and E2. Oh, my bad. SN1 and SN2.
SN1 and SN2. On this carbon right here, what do you think? Do you think it's going to be SN2 or SN1 that happens right here?
SN2.
Why you say that? You're right. I agree.
Because
What type of carbon is it? Is it primary? Is it secondary? Is it tertiary?
It's primary. Ooh, primary.
So that means that what? Primary carbons mostly do what? SN2 substitution. Is that right?
Yes.
Which one of these is your nucleophile? Would it be the oxygen or would it be this carbon right here?
The carbon.
Are you sure about that?
Hold up.
That the carbon you just said was going to get substituted, right? But does the carbon?
It's oxygen.
It's the oxygen. Doesn't the oxygen have lone pairs on it? Let me see if I could draw some in with my little bootleg annotation tool. Yeah, I need to draw. Doesn't the oxygen have lone pairs like that?
Yep.
And does this carbon have any electrons?
No.
No. So it can't be the can't be the nucleophile. It's got to be the electrophile. Is that right? What is bromine in this reaction?
The leaving group.
Leaving group. You see, all this stuff is not just fairy tale stuff, right? It's real live chemistry that happens every single day in labs all around the world, right? So this is a SN2 type substitution. Excuse my handwriting. It's bootleg, but you get the point. All right, it's a SN2. Just like this is an osmolation, something that we just studied. All right, any questions about that? Oh, hold up. Okay, there we go. All right. So in this particular reaction at KH, it serves as a base. So it'll pull off this proton, do a proton transfer here, make oxygen negative, and then boom, you attacking the bromine and kicking it off, right? All right. Now let's talk about another synthesis. This is actually uh, cocaine. This is what the cocaine molecule looks like. The reason why it binds, how it binds in your brain, is because of this nitrogen right here. That nitrogen is the structure is similar to dopamine, right? So where the dopamine receptors in your brain, you know, the happy receptors that make you feel good, the nitrogen from cocaine can bind to that same receptor. And that's why you get that euphoria, that excitement, you know, you get hyped up after using it because it binds to the same pleasure receptors like the dopamine receptors. All right. So cocaine by itself, you take it from the coca leaf, right? And the extraction process involves taking the leaves from the coca plant, putting them in a big barrel or a bin, covering them with ether, and then have someone stomp them. That's the old way. Have a person who's in Peru or Colombia or Honduras or wherever stand in that vat and stomp on those leaves for hours and hours and hours and hours until they get the extract, the coca extract. What they extract out is not what you see here, but it's a salt, right? This nitrogen, and if you were to take the cocaine extract directly from the coca plant, what you get is, let me see if I can move this toolbar out of the way. What you get is this, got a long pair on nitrogen, and then it's coordinated to an HCl molecule. That C is terrible. Get back. So HCl, it's a HCl salt. So it's cocaine hydrochloride, right? That's what you first extract. But when you sell it to somebody who wants to triple their money, right? Because a kilo is anywhere between 15 and this is old numbers. It may be much more expensive now, but before somewhere between $15,000 and $20,000 per kilo. If you want to quadruple that or multiply that by 10 times, you would take the powder and turn it into crack. So the way you do that is to take the cocaine hydrochloride and then add baking soda to it, right? The baking soda removes the HCl, right? So you take it, you add baking soda, you heat it up on the stove top in a double boiler, right? You got a jar with your stuff in it, and you got a pot of water boiling. And as it heats up, there's a reaction taking place that where the baking soda is reacting with the HCl. And once you remove it, what's left is the cocaine in this what we call is base form, right? That's where the term free base comes from, because you're free in the base. You take the HCl, you add baking soda, right? And then you free up the nitrogen. So that's why they call crack free base, or that's why they used to call it that, right? Back when people first started using the rock form of cocaine, it was called free basing. All right. So here's what cocaine looks like, right? One reaction, let me close that out. One reaction that um, one reaction is shown down here, right? How do I get this nitrogen methylated, right? And the way to do that is to use a simple substitution reaction. You take the cocaine itself, and let me go back. This has been synthesized in the lab before. It was synthesized by Tuffarello, 1979. One of the things about doing lab work on drugs like cocaine, like morphine, heroin, methamphetamines, anything like that, you have to have approval through your university. You're not doing this in your garage when you go to prison. You got to have approval through your university by the DEA. So if you order any, and the DEA has a database of compounds that have been used to synthesize certain drugs. So if you order anything on that list, you're getting a phone call from the DEA, and you got to fill out a ton of paperwork. And what you have to end up doing is telling them who you are, what university you are affiliated with, what your research entails, and why you need this particular compound. That's happened to me before. We wasn't making cocaine, but we were using one of the precursors to it. And I got this phone call after I placed the order. They called the university, they tracked me down, and they wanted to ask me all these questions about why I needed this specific compound. So when you make drugs in an academic setting, and if it's a controlled substance, then it has to be DEA approved. Your work has to be basically approved by the DEA, that you're not making this to go sell it, around the corner from your wherever. All right. But how do you methylate that nitrogen? The way you methylate it is here, right? You take nitrogen, you treat it with methyl iodide, and you do a substitution. What type of substitution is that, do you think? And which one is the nucleophile and which one is the electrophile? All right. Wouldn't the nitrogen be a nucleophile because of the electrons that are able to be donated? And then that will make this your electrophile, right? So that's how you methylate that nitrogen. All right. So let's look at the synthesis, the actual cocaine synthesis, or part of it anyway. All right. So this first reaction is what you call a cycloaddition, right? And it's exactly what it sounds like. You add two pieces together to make a ring. That's what the cyclo part means. So cyclo meaning ring, and addition meaning the type of reaction you did to create or generate the ring, right? So you can see here, it's going to be this oxygen, this nitrogen, and this carbon. That's 3 atoms. And then these 2 carbons over here, that's 2 atoms, to give you a 5-member ring that you see right here. All right. And the way that works is, again, everything goes back to the same basic principles. Nucleophiles and electrophiles, donors and acceptors, sources and sinks. Everything in organic goes back to those principles, right? So if you look here, this oxygen is nucleophilic, and it's going to donate a pair of electrons to this carbon, right? Which is electrophilic, all right? And so this intermediate is what you get from that addition reaction. Notice I didn't say that it's a substitution. I didn't say that it was an elimination. It's an addition, because I'm taking the oxygen and I'm adding it to a pi bond. And that's what addition reactions are. It's when you add an atom or a functional group or a molecule to a pi system, right? So with this intermediate, can somebody tell me where the nucleophile is in this intermediate?
On the CH2.
It's right here. That's exactly right. And where's my electrophile? What do you think? Think about the product. I'm trying to make a 5-member ring. So which one of those 2 atoms do you think that CH2 is going to attack?
The N plus.
Okay, that's a good assumption. But again, I'm trying to make a 5-member. If it attacked the nitrogen, it'll be a 4-member ring. But I'm trying to cyclize this to a 5-member ring. This carbon is more electrophilic. It's a more electrophilic site. Even though the nitrogen is positive, it's going to attack here, right? So let me ask you another question. This part of the reaction, right, is that inter or intramolecular? Intermolecular or intramolecular? Which one? What do you think?
Where the carbon is?
Yeah, it's intermolecular. That's right, because this is 2 separate molecules reacting together. Are you following? What do you think the intermediate cyclization part is going to be? Inter or intramolecular? Look at the arrows for the cyclization. So this is attacking this carbon, and this pair of electrons in the pi bond is going here to nitrogen. What do you think? Inter or intramolecular?
Intra.
Intra, right? Intra means internal. Is that right?
Yes, sir.
And inter means external. So the previous reaction right here to get to the intermediate is intermolecular, but the actual cyclization of the intermediate is intramolecular. So you can see over here with everything that we've seen, we've studied before. This is a polar mechanism as opposed to a radical mechanism, right? It's heterogenic bond formation, heterolytic bond cleavage, right? You got nucleophile here, you had a nucleophile here with oxygen, and then in each case, the nucleophile interacted with an electrophile that was either positive or partially positive. So what we've been studying is not esoteric. It's not pie in the sky, like only on paper and only in the examples that we've been doing in class. These are real reactions that happen every single day. All right, so let's look at another part of the synthesis, right? You have another fragment. This is the precursor to the cocaine molecule. And notice I'm going from here to here. What changed?
You created a double bond.
Made a double bond. Kind of gave it to you right here, but I made a double bond. That's right. How do I make double bonds? Tell me one. If I gave you 4 types of reactions, which we talked about, what are they? The 4 different types of reactions. Substitution, elimination, addition, and rearrangement. Is that right?
Yes.
All right. What type out of those 4 reactions, which type is used to make double bonds?
Elimination.
Elimination. So what do you think happens between here and here? Some kind of way I did an elimination. Is that right?
Yes.
What type? Because we talked about 2 types. Is that right? We talked about E1, we talked about E2. If I told you that DBN was a strong base, what type of elimination would you suggest in the presence of a strong base? Right. Let me ask it this way: does E1 need a strong base? Yes or no?
No.
No, it doesn't. So the presence of a strong base indicates that it's an E2 elimination, right? So let's walk through that part of the synthesis, right? You have an OH group here that's a really terrible leaving group. So what I need to do is make it a better leaving group. And one way to do that is to treat it with what's called a mesyl chloride or methane sulfonyl chloride. That's this molecule right here. So the alcohol basically adds to the sulfonyl, and it's like an addition/elimination, right? And so this is what you end up with. We call this, let me see if I can put some text down here. We call this a mesylate. Right? That mesylate, what I've done in essence is made the alcohol a better leaving group. So my elimination is faster, right? I can't eliminate with just OH. I got to do something to it. I got to either do a proton transfer to it, or I have to put some other functional group on it to make it a better leaving group. But the reason I didn't just use water or acid, this is very important, is because I may have other functional groups in that molecule that I don't want to react, right? And so I want to pick my reagents according to what I'm trying to do. That's why they chose the mesyl chloride and DBN and not just dump in some water or some sulfuric acid or something like that, because what you end up doing is ruining some other part of your molecule. All right, so that's a really strategic choice to use mesyl chloride. All right, so let's go to the next slide. We can see here, now this proton right here, you're dealing with pKa, has a pKa of 14.2. Is that bad or good? (14.2 pKa). And what does pKa refer to? Anybody? Doesn't pKa refer to acidity? How acidic or non-acidic a proton is? Is that right?
Yes.
All right. 14.2 is not a horrible number. That's actually that's a decent pKa, and you can pull that proton off with a strong enough base. Notice, I want you to notice something. What type of proton is that? Does anybody remember when we were studying pKa and we talked about protons that were next door to a carbonyl? Anybody remember that? This is sloppy, but it's not as bad as it could be. Yeah. Nobody remembers what we call a proton that's next door to a carbonyl or next door to a leaving group. Anybody? Don't we call them alpha protons? Right, so that alpha proton is 14.2 because when I pull it off, right, I can actually, I wish I could copy that. I can. Or maybe not. When I remove it, right, I get this. And then, let me see if we can work from that. Right, I'm going to get this. And that carbon is going to be negative. How can I stabilize that charge, that negative charge? Right? Think about Hires.
Resonance?
It can be stabilized through resonance. That's exactly right. I can do this, can't I? I can take this pair of electrons and push them here. And I can take this pair and push them up on the oxygen. Is that right? So that's why that proton has a pKa of 14.2. Because the conjugate base, after I treat it with this DBN, the strong base, is stabilized by resonance. All right. So this is how the elimination part works. So DBN comes in, boom. You push this pair of electrons here to make the pi bond, and then you lose the mesylate. Now here's another question. We already agreed that this is E2. Is that right?
Yes.
Is it concerted or stepwise?
Concerted.
It's concerted. That's right. It's concerted. All right. All of this stuff is not new. This is stuff we've already studied. All these, not the actual compounds, but the methods used to get to those compounds. We've seen all this stuff before. All right. All right, let me close that and go to the next slide. All right, so this is the overall synthesis for that elimination part. So first you treat the alcohol with mesyl chloride, then you add the base to eliminate. It's an E2 type elimination. It's all your bond cleavages are heterolytic, all your bond formation heterogenic, and it's a polar mechanism. All right, I got 7 minutes. Let me see. Y'all want to do this one? We'll stop with this. So this is deoxytetanilide, the plus 13. The plus is in relation to its optical activity. That's a stereochemical concept. Do you see how all these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you got 11 chiral centers on this thing, or 11 stereo centers. What that means is that you have 11 atoms that are chiral. Specific 3D orientation. That's what that means. Right, so you got 11 atoms in that molecule that have a specific 3D orientation. Right? Call those stereo centers. Everywhere you see a wedge or a dash, we call that a stereo center. And so what that means, the plus 13 means that this is the plus isomer. And then if there's a plus isomer, then it has to be a minus isomer also. Well, the number of isomers actually is 2 to the 11, because you got 11 stereo centers. And if you want to determine how many isomers are possible, it's 2 to the n, where n is the number of stereo centers. So you got 2 to the 11 number of stereo centers. That makes synthesizing this more complicated, because that means you have, I don't know exactly what that is, if it's 2 to the 11 power, something in the millions though. So you got millions of possibilities for these stereo centers and their configurations. So, but you need this one, right? So that makes synthesis that much more difficult, and it makes being able to make these compounds that much more impressive when you can make one isomer out of millions of isomers that are possible. All right, but let's look at some of the fragments. So this is one of the fragments used to make this natural product. And if you look here, what reaction is that? Right here. Right. It's actually this double bond that's reacting. Can you see that right here? So what product did I make from that reaction?
Diols.
A diol, right? So this is, again, the reaction is up here. It's osmolation. But I made a diol from that, right? And then the other part over here, so it's what we call a diol cleavage. Right? And that is using sodium periodate. So basically what you do with sodium periodate is you oxidize, you cleave the diol right here. Right, so you're gonna break this carbon-carbon bond right here. And each carbon is gonna get oxidized up to a carbonyl, right? So that sodium periodate, that's used for what we call cleavage, diol cleavage. So that's how I get this aldehyde right here, because this diol that's shown right here, well, this alcohol, I'm sorry, that's shown right here is gonna get oxidized up to a carbonyl. So that periodate cleavage is kind of like ozonolysis, but instead of the star material being an alkene like it is for ozonolysis, it's actually a diol, but the outcome is the same. It's the exact same. Both carbons in the diol get oxidized up to carbonyls. All right, and then if you look right here, here's my alkene, here's my product. Right? How do I make alkenes from alcohols? Well, I can do hydroboration. What's the other way?
Oxymercuration.
Either one works, right?
Mm-hmm.
What's the difference?
The stereochemistry,
Not stereochemistry. What's the other term we use?
regio.
The regiochemistry, right? So that means for this double bond, the alcohol can be what? It can be here. Let me change the color right quick. I can put it here, or I can put it here. Is that right?
Yes.
It can be Markovnikov addition or anti-Markovnikov. Which one is hydroboration? Which regiochemistry does it follow? Anti-Markovnikov. That's why you see the OH. Let me erase this. That's why you see the OH here on the least substituted carbon, right? Are y'all following? Right there. And not on this carbon because I used hydroboration. Oh, sorry. All right. Any questions about that? No questions. All right. I see we lost 3 people too. I guess this was boring, but that's okay. We're gonna stop here, and I'm gonna upload this recording to Blackboard. I'm not Blackboard, YouTube, and I'll upload the PowerPoint to Blackboard.
I had a question, but it was about something in the PowerPoint that was earlier.
Okay, go ahead.
When it was like the N plus nitrogen and then the carbon, and you said the carbon was more electrophilic. What did they use like to determine that?
You mean like right? Let me see. It was right here, right?
Yeah.
Okay, so a couple of things, right? Number one, the nitrogen is bonded to oxygen. And so the dipole going this direction is huge, right? But nitrogen already has 4 bonds and it can't make more than that. And the fact that even though it's positive, it doesn't have any room to accept a pair of electrons. Are you following? Not another pair. So the carbon is going to be, in this case, more electrophilic because the dipole is going to be moving this way. You got a positively charged nitrogen that's sucking electrons towards itself, and you got this oxygen that's sucking electrons that way. So it makes that carbon partially positive and is more accessible. And so that's where that carbanion is going to attack.
Why doesn't it have any room?
You got to think about the orbitals. It's got a full octet, right? So it's got a full octet. And if you add a pair of electrons to it, it's going to have 10 electrons and not 8. And that's not possible. Because think about when you add in electrons or you donating electrons, you got to think about the orbitals that make that atom up and where that atom will be able to accept a pair of electrons. And so the carbon is more apt to accept a pair of electrons than the nitrogen because of the fact that the carbon is sp2 hybridized, right? And so you have carbon, the other carbon can donate a pair of electrons to that because of the pi bond and because of the sp2 orbital or the unhybridized p orbital that's present, and then the sp2 orbital that has one single electron in it, right? So it's all about the orbitals and whether or not the orbitals are filled or half filled or unfilled. But a positively charged nitrogen is not a good acceptor.